Hello and welcome back to another video. Today we're going to discuss chapter 4, which is on continuity. I make the document myself, a summary of chapter 4, as you can see here, just to avoid issues with the owner of the book. And my name is Taha Arkian. I will give you this lesson today. It's the fourth video I'm making. I hope you will enjoy it. So let me just zoom a little bit, just check if I'm recording. Yes, okay. So we're going to talk about continuity in this chapter, and the first thing you want to see is the limits of function. So let's read this definition. Let x and y be metric spaces. Suppose e is an x, and let f go from e to y be a function. If p is a limit point of e, we say that f of x approaches q as x approaches p, and we write limit as x goes to p of f of x equals q to indicate this limit. And if we continue this definition, we're going to say that there exists a point q in y with the property that for every epsilon greater than 0, there exists delta greater than 0, such that dy f of x q is less than epsilon. And for all x and e, satisfying 0 is less than dx xp less than delta. So what this means here, if we want to look at it closely, one important property of this limit is that it approaches a limit point p. It must be a limit point. This is really important. And the reason why it must be a limit point is that when you get smaller and smaller epsilons, you can get smaller and smaller deltas, right? And if you want to get smaller and smaller deltas, it must be a limit point, because we want to have points that are actually lying in this delta, else it won't work, right? So that's what we're doing here. That's why we're talking about limit points. And basically, another important property is that if it works for an epsilon that is greater than another epsilon, then it works. If it works for a smaller epsilon, it works for a greater epsilon too, because it's part of it. Because if it's smaller, if the neighborhood you're taking for the y-axis is smaller, then that smaller neighborhood is included in that bigger neighborhood, so it will work for every other neighborhood that contains this neighborhood. So that's why we really emphasize that epsilon is something that goes close to 0. Here the x and dy denote the metrics in x and y respectively, okay? Yeah, this is really important. Note that p lies in x, but it is not required to be in e. Even when p is in e, it is possible that f of p is not equal to limit as x goes to p of f of x. Yeah, exactly, because the important property is that it is a limit point, not necessarily a point of e. Because if we want the limit to work, it must satisfy this, and if we want this to be satisfied, all we need is that it is a limit point. So if this is all we need, it doesn't necessarily need to be part of e, because limit point is not always part of e, right? And this is why we also get that f of p is not necessarily the same thing as limit as x goes to p of f of x. We have the following theorem. Let x, y, e, and f and p be as in definition 4.1, then limit as x goes to p of f of x equals q if and only if limit as n goes to infinity of f of p of n is equal to q for every sequence pn in e, such that limit as n goes to infinity of pn equals p for all pn not equal to p for all n. And I will explain the proof strategy later, so I'm just going to explain the proof for now. Assume that that limit x goes to p of f of x equals q. Take any sequence pn in e, satisfying limit as pn goes to infinity goes to p, and pn not equal to p. For any epsilon greater than 0, choose delta greater than 0, such that dy f of x q is less than epsilon. So because we're talking about a limit here, so we want to take it to be like this as a definition, right? So we take this. Since Pn goes to P, there exists n such that 0 is less than dx Pn less than delta for all n greater than n. Uh, yeah, because this thing, uh, it gets smaller and smaller as it approaches. We know it approaches, and we know when it approaches that certain value, the distance can be limited, as we saw in chapter 3, right? In chapter 3, when we talked about limits of sequences, we said that it's whenever for it's the definition was for all epsilon greater than 0 there exists a number n such that for all n greater than n, the sequence minus that number is less than epsilon. And this is the sequence minus that number, and it's supposed to be less than epsilon. But if it's less than epsilon, we can take it to be less than delta too, right? Because epsilon can be smaller than delta. Therefore, dy f of p of n q is less than epsilon. For n greater than n, proving the forward implication. So, yeah, because it lies in this neighborhood. This Pn over here, this Pn lies in this neighborhood. So we know that this neighborhood is related to this other neighborhood in y-axis, right? And if it lies in this neighborhood and it's related to this neighborhood, then taking the function will make sure function of p of n will make sure that it lies in this neighborhood. So basically, you're evaluating Pn at and P at f with f to get it to come at this neighborhood, right? And you're going to get dy f of p of n q is less than epsilon for all n greater than n, which proves that when the limit goes to q, that means the sequences go to p. Conversely, suppose limit as x goes to p of f of x is not equal to q. Then there exists epsilon greater than 0 such that for every delta greater than 0, we can is it for every delta? I'm not sure. Let me just check. Yeah, for every delta greater than 0, there exists a point x in E with 0 less than dx xp less than delta, and dy f of x q greater than or equal to epsilon. Because this is basically the contrary of what we're saying. If it doesn't go to q, then we just flip the inequality signs and we're getting the inverse of what it's saying, right? Choosing delta n equals 1 over n for n equals 1, 2 to infinity gives a sequence Pn satisfying Pn goes to P, for which the limit as n goes to infinity of P of n, f of P of n is not equal to Q. Just to make sure over here. Yeah, so exactly. So We're saying that if it doesn't go to Q, then this neither goes to Q. It's impossible that this goes to Q if this doesn't go to Q. And we do this by choosing delta n equals 1 over n, right? And suppose that instead of x over here, we take p of n, right? And here we take f of p of n. Then it gives it gives a result, right? Let me just think about this a little second and I'll come back. Okay, so I'm back. I got a little confused here because I was thinking, why did they choose 1 over n over here? But I realized it's just you can choose any other function that goes to 0 and you can get the same result. Let me explain it to you. Let me just check first. Okay. Because we know that this statement is there exists epsilon greater than 0 such that for every delta greater than 0 we can find 0 less than dx xp less than delta implies this, which is basically if you take the not of the initial statement, if you take the contrary of the initial statement, right? And if we take delta n equals 1 over n for each p of n, so x is equals p of n, that means p as you let n go to infinity, delta goes to 0 and the distance between p of n and p goes to 0, which means it converges to p. That means this is true over here. But this is not true because we said that it doesn't satisfy this, right? And since it goes to p over here, as p of n goes to infinity, this approaches p, right? But we know that this is false over here, so that means it won't go to q either, and that proves the statement. If f has a limit at p, then that limit is unique. That follows from theorem 3.2b and 4.2. Because in chapter 3 we showed that each limit point is unique. Let me just read the theorem from chapter 3 just as a refresher. Yeah, if p is an x and p prime is an x, and if pn converges to p and to p prime, then p prime equals to p. That's the statement for 3.2b. And now we can define the sum of functions and their limits, etc. Like this. This is theorem 4.4. This is analogous to adding limits of sequences because we just proved that it's the same thing as a function of a sequence. So it gives the same results. Now, this is really important. Now we're going to talk about continuity. Let x and y be metric spaces, e and x, p and e, and f goes from e to y. We say f is continuous at p if for every epsilon greater than 0 there exists delta greater than 0, such that dy f of x f of p is less than epsilon for all x and e with dx xp less than delta. What this is saying basically is that the limit as x goes to p of f of x equals f of p, because we just replace uh, p with f of p over here, right? Sorry, we just replace the limit with f of p over here. That means the limit goes to f of p. Okay, let's see what it says here. Yeah, because if it is an isolated point, if you take you can choose a delta such that in that neighborhood you only have that isolated point, right? So x equals to p, and if x equals to p, the distance is equal to 0, which is less than epsilon. So obviously, if you have an isolated point, it's automatically going to be continuous. In the setting of definition 4.5, suppose p is also a limit point of E. Then f is continuous at p if and only if limit as x equals to p of f of x equals f of p. This is what I was talking about earlier. So it's pretty obvious. Just take from previous theorems. Now we have the following theorem. Let x, y, z be metric spaces. Suppose E is an x, f goes from E to y, and g goes from f of E to z. Define h goes from E to z by h of x equals g of f of x. If f is continuous at p and E, and g is continuous at f of p, then h is continuous at p. The function h is called the composition or composite of f and g, often written as h equals g o f. Now for the proof. Okay, let me just go back to this theorem over here that we proved. I forgot to explain the strategy over here. This strategy is really important. The strategy is basically just to take the definition of the limit and the definition of the limit of a sequence and relate them together for some value n greater than n. And here likewise you do the same thing by letting delta go to 0 and showing that if this is not true, this is also not true. That's the strategy. Okay, let's just go back to this theorem. I'll explain the strategy later. Let epsilon be greater than 0 be given. Since g is continuous at f of p, there exists eta greater than 0 such that distance z, gy, g of f of p is less than epsilon. Because y is the domain of g, right? And f of p is the limit point at which we're evaluating g, right? And that means this is less than epsilon because that's the definition of continuity. Whenever dy y f of p is less than eta. This is from the previous function because yeah, this is the neighborhood for which this is associated, right? And y is an f of e. Since f is continuous at p, there exists delta greater than 0 such that dy f of x f of p is less than eta. Basically, y is equal to f of x if you look at it closely. Whenever dx xp is less than delta, basically the strategy, I'll explain it now, is you're taking some sort of chain. So the epsilon over here and the delta over here, this becomes the epsilon over here, this becomes the delta over here, and you can relate them together, right? it follows that dz h of x h of p is equal to dz g of f of x g of f of p is less than epsilon. Okay. A function f from a metric space x into a metric space y is continuous on x if and only if f inverse of v is open in x for every open set v in y. Now, a really important part of this is that this is for f inverse of v, not for f of v. What we'll see later is that there are a class of functions called open functions, for which every set you take in the domain which is open, you're going to get an open set in the codomain. But here we're talking about an open set in the codomain which is associated to the domain. So this is not necessarily an open function, it's just continuous. This provides a very useful characterization of continuity, okay? To prove it, I'll explain the strategy. Assume f is continuous on x and let v in y be open. We must show that every point of f inverse of v is an interior point. Let p in x with f of p in v, with f of p in v. Since v is open, there exists epsilon greater than 0, such that y is in v whenever dy f of py is less than epsilon. Because it is a limit point, it's an interior point. It's open, it's an interior point, that means it must have a neighborhood contained inside inside v, and this is a neighborhood contained inside v, and you can take it to be less than epsilon. By continuity at p there exists delta greater than 0 such that dy f of x f of p is less than epsilon whenever dx x3 is less than delta. This is by continuity. We're just taking the definition of continuity. This implies that x is an f inverse of v whenever dx xp is less than delta. So this over here, f of x f of v is less than epsilon. So okay, so basically let's finish reading this. So p is an interior point of f inverse of v. What this means over here, okay. When you take the inverse of a function, what you're doing is you're taking the point and you're flipping its x coordinates with the y coordinates. So if you have a point AB, it's going to become a point BA, right? And basically, the distance between AB and BA is the same thing over here, basically what it's saying. See, here we have dy f of b y. F of b is a, y is b. Y is f of x, right? Here, this is BA. See, it's flipped. The order is flipped. There exists delta greater than 0 such that dy f of x f of b is less than epsilon whenever dx xp is less than delta. Right. Exactly. So you're flipping the order, which means that x is an f inverse of v. So p is an interior point of f inverse of v. Let me just double check. I'm just checking real quick. Yeah, it's like that. This V is open, hence f inverse of V is open in X. Okay, sorry. Let me start from here. Conversely, suppose f inverse of V is open in X for every open V in Y. Fix P in X and epsilon greater than 0. Let V equals Y in Y, dy y f of B is less than epsilon. Okay. Conversely, suppose f inverse V is open. Fix P in X and the epsilon greater than 0 such that distance between Y and f of P is less than epsilon for Y and Y. So you're taking a neighborhood of f of P with distance epsilon. This V is open, hence f inverse of V is open in X. Thus there exists delta greater than 0 such that X is an f inverse of V such that distance of X xp is less than delta. Give me a second, I'll come back. Sorry. Okay, let me restart rereading this proof because I was wrong. Let me just check. Okay. A function f. Okay. So I was wrong about the ABBA thing. It's close, but I was wrong about it. I'm going to explain in more detail. Assume f is continuous on X and let V and Y be open. We must show that every point of f inverse V is an interior point. Let P and X with f of P and V. Since V is open, there exists epsilon greater than 0 such that Y is... The definition of an open set is that its distance is less than something, not less than or equal, right? So we can describe it like this. By continuity, there exists delta greater than 0 such that dy f of x f of p is less than epsilon whenever dx xp is less than delta. And this implies x is in f inverse v such that whenever dx xp is less than delta. What this means over here okay, this x is associated with this neighborhood over here, which is analogous to this neighborhood. Okay, so if we want this to be less than epsilon, that means if we want it to be open, to be less than epsilon, this must be less than delta. If it's less than delta, that means it's open, right? Because we're taking a distance to be less than something, not less than or equal to something. That means it's open. So we're taking an open set here. We're taking the definition of continuity and we're associating it to another open set here. That's the strategy. Take an open set, take the definition of continuity associated with another open set, and show that the associated open set is open, right? This implies x is an f inverse of v whenever dx xp is less than delta, so p is an interior point of f inverse of v. Conversely, For the converse, we want to prove that it is continuous if it is open for every x, right? Conversely, suppose f inverse of v is open in x for every open v in y. Fix p in x and epsilon greater than 0. Let v equals y in y dy y f of p is less than epsilon. So this v over here, this is the general v we're talking about. Now we're taking another v. So it's going to be an open set in the y-axis, right? It's going to be an open set in the y-axis, and since it's an open set in the y-axis, we just proved right now in the previous result over here that if it's in the y-axis, it's open in the x-axis too. So f inverse of v is open in x. Thus there exists delta greater than 0 such that x is in f inverse of v whenever dx xp is less than delta. If x is in f inverse of v, then f of x is in v, meaning that dy f of x f of v is less than epsilon. Yeah, because that's how we defined it. Every point of f inverse of v, if you take its function, is going to be in v. Meaning that distance of f of x f of p is less than epsilon. Because it's in that set over here, and it's the definition of this set over here. And we know this happens whenever dx xp is less than delta, because f inverse of v is open, so we can take a delta not less or equal to delta. Instead, we take less than delta to define as an open function, and that's how we prove it. And the strategy for the second part is that you want to use the result we got from the first part and take an open set in the y-axis, which results in an open set in the x-axis, and since it's open and its function goes to the same thing in the y-axis, you can show that it's the same thing as the definition of continuity. So that's the strategy. Now we get the following corollary. A mapping f from a metric space x into a metric space y is continuous if and only if f inverse of c is closed in x for every closed set c in y. This is because if you take the complement of the function is the same thing as taking the complement of the set of that function. Now we have the following theorem. Let f and g be complex valid continuous functions on a metric space x. Then f plus g, f times g, f over g are continuous on x, with understanding that g of x is not equal to 0 for all x in x in the last case. So the proof is at isolated points of x, the result is immediate. At limit points, the statement follows from theorems 4.4 and 4.6. It's pretty, yeah, it comes from the previous theorems, and it's pretty obvious because you just showed that addition and etc. for limits it works, and since continuity has to do with limits, it must also work. Now I have the following theorem. Let f1 to fk be real valued functions on metric space x, and define f from x to rk as the following. Then f is continuous if and only if each component f1, fk is continuous. And b, we have if f and g are continuous functions from x into rk, then f plus g and f dot g are continuous on x. Here f plus g is a mapping into rk, while f dot g is also a real valid function x to f of x dot g of x. Now, this, if you remember in chapter 3, we had a similar proof that if you want a vector to converge, each of its components must converge. And basically, we do this by saying that if you take the difference between the components is going to be less or equal to the difference between the addition of the components when you take their square roots, because it's going to be definitely going to be a value added to that component, and you're going to square those and take the square root, and you're not just taking the square root of that initial square, you're taking this square root of all the other components squared, so that it's going to be greater than nor equal to the components, to the difference of the components, which means that this this thing over here, f of x minus f of y, if it's less than epsilon, then this is also less than epsilon, and that completes the proof. And for f plus g and for f plus g and f dot g is very similar, because we use A together theorem 4.9, which was basically this over here. You're just adding the components together, so it must give you the same thing. So now we have the following example. Let x1 to xk be the coordinates of a point x in Rk. Define the functions phi ix equals xi. These are called the coordinate functions since phi ix minus phi ix minus phi iy is less than or equal to x minus y, because it's component wise, right? We just showed that when you take the components together, it's going to be less than or equal to taking the actual thing in the difference. We may take epsilon delta equals epsilon in definition 4.5, show that phi I is continuous on Rk. So yeah, exactly. If x minus y is less than delta, right? That's the neighborhood in the domain part. If you take it less than delta, that means this is also less than delta. So you can just take delta equals epsilon over here, right? Now, by repeated application of theorem 4.9, every monomial of the form phi 1x and n1, phi 2x, n2, etc., where n1 and k are not phi. I don't know why I put phi's over here. Just take x to the n1, x to the n2, etc. Every monomial like this is continuous, and their addition is also continuous. So every polynomial is continuous. And rational functions are also continuous when you have a non-zero denominator. And px equals the absolute value of x is a continuous real valued function. And if f is continuous, this is from the triangle inequality, right? Because the absolute value of the absolute value of x minus the absolute value of y is less or equal to the absolute value of x minus y. So here again over here you can take delta equals epsilon to get the result, because it's less than or equal to the domain part. If f is a continuous mapping from a metric space x into Rk, we define phi p equals the absolute value of f of p. It follows from theorem 4.7 that phi is a continuous real function on x. We have defined continuity. Okay. Now we come to continuity and compactness. A mapping f from E to Rk is said to be bounded if there exists a real number m greater than 0, such that the absolute value of f of x is less than or equal to m for all x in E. That's what we saw in chapter 2 for the definition of bounded functions. Sorry, but for bounded sets. Now, if f is a continuous mapping from a compact metric space x into a metric space y, then f of x is compact. And the reason for this, the strategy is, if you take an open cover here and an open cover here, you know that they're open. And we just prove that if this is open, this is open. So if the codomain is open, the associated domain part is also open. So that means there's also going to be an open cover for it. That's a strategy over here. Let's read the proof. Let VA be an open cover of f of x. Since f is continuous, theorem 4.8 tells us that each f inverse of VA is open in the x. Yeah, because X is compact, there exist finally many indices alpha 1 to alpha n such that X is an F inverse of V alpha 1 all the way to F inverse V alpha n. Since F of F inverse of E is inside E, for any E in Y, it follows that F of X is in V alpha 1 unions all the way to V alpha n. Thus, F of X is compact. And you can show this with a few examples. When you have a continuous one-to-one function, F inverse of F of E and F of F inverse of E are supposed to give you E. But if it's not that the case, you can just take an example and show that this is inside E and E is inside this. So the order matters whenever it's not one-to-one. If F is a continuous mapping from a compact metric space X into Rk, then F of X is closed and bounded. This follows from the Hein-Borel theorem. Basically the same thing as this, but applied with the Hein-Borel theorem. Now let F be a continuous real valued function on a compact metric space X. Then there exists points P, Q, and X such that supremum of X and X of F of X equals F of P. M equals infimum of X and X of F of X equals F of Q, where M is the least upper bound and M is the greatest lower bound of the set. The conclusion of 4.16 now, okay. So basically, if it's on a compact metric space, you can define a maximum and a minimum value. And the proof is very simple. It follows from the theorem that says that every set of every segment in the real number line, if it's closed, it's going to contain its supremum. And we know that it's closed and bounded by the Hein-Borel theorem when it's compact. So it contains both M equals supremum of F of X and M equals infimum of F of X. And these are achieved at some P, Q, and X. Theorem 4.17, let F be a continuous one-to-one mapping of a compact metric space X onto metric space Y. Then the inverse mapping F inverse Y to X is defined by F inverse of F of X equals X. This is what I was talking about earlier. So the proof is, applying theorem 4.8 to F inverse in place of F, it is enough to show that F of V is open for every open set V in X. Let V be an open set in X, its complement V complement is closed in X, hence compact. By theorem 4.14, F of V complement is compact in Y, and therefore closed. Since F is bijective, F of V is a complement of F of V complement, and thus F of V is open. So the strategy over here, you know that it's compact and it's one-to-one, it's a continuous one-to-one mapping, and you know that for each F inverse, when you take open sets, you're going to get open sets, and if you take closed sets, you're going to get closed sets. So for any set you take, you can set the limits of those sets, the limit points or the boundaries of those sets, to be the desired points you want. And you can show that those desired points are associated to the other desired points. And since it's bijective, you're going to get that this desired point is the same thing as that desired point. So taking F inverse of F of X will give you X. That's the strategy, and we just explained the proof. Now, definition 4.18, a mapping F from a metric space X into a metric space Y is said to be uniformly continuous on X if for every epsilon greater than 0 there exists delta greater than 0 such that F of P, F of Q is less than epsilon whenever P, Q, and X satisfy dx PQ is less than delta. That's for uniform continuity. Now, a really interesting thing, that for continuity at a point P, the delta in definition 4.5 may depend on both epsilon and P. For uniform continuity, a single delta works for all points P and X. So The reasoning is that uh, when you choose epsilon and p, you don't need to choose any more than one delta value, because all you need is one neighborhood where p and q is one distance between p and q. All you want is one distance, so you only need one delta when you choose epsilon and p. Okay, so we have the theorem for 4.19. Let F be a continuous mapping from a compact metric space X into a metric space Y, then F is uniformly continuous on X. So if it's continuous, that means it is uniformly continuous. That's what it's saying. Now let's prove this. Okay. Let epsilon be greater than 0 be given. Since f is continuous for each p in x, there exists phi p greater than 0 such that dx of x pq is less than phi p. And you're basically choosing some sort of neighborhood for pq by calling it phi p. Implies dy of ffp ffq is less than epsilon. Now define j of p equals q in x such that the xpq is less than 1/2 phi p. So you're taking something inside this dxpq and you're calling it jp, and it's basically having half of the distance that you're defining. And since p is in jp, the family jp p and x forms an open cover of f of x. Because x is compact, there exists a family finitely many points p1, pn, and x such that x is in jp1 unions all the way to jpn. Now we set delta equals 1/2 minimum of phi p1 all the way to phi pn. Okay, so you're taking an open cover, and now you're going to take the minimum of those of the distances of those open covers, and you're taking half of it. And the strategy here is that you want to add it with the other half and show that it's going to be less than epsilon. So now let p, q, and x satisfy dx pq less than delta. And we know that this set delta greater than 0 exists because the minimum of a finite set of positive numbers is positive. Now let pq and x satisfy the distance of x pq less than delta. By the finite covering, there is some m in 1 to n such that p is in jpm. Yeah, okay. Because it's covered, so at least one of them will have p. So dx p of m is less than 1/2 phi pm, because that's the definition of the j sets over here. Also, distance of xq to pm is less than or equal to distance of xpq plus distance of xppm from the definition of the metric spaces. Distance of xpq says less than or equal to phi p, and distance of ppm we said is less than or equal to 1/2 phi pm, right? Now let me just see what's happening over here. I'm not sure why this is delta over here. Let me just think about it. Delta is equal to this. PQ. Oh, okay, no, sorry. We're mistaking this PQ with this PQ over here. Now let PQ and X satisfy dx PQ less than delta. So we chose new points P and Q. So we're going to have this. And since delta is equal to 1/2 the minimum of this, and PM is going to be greater than some point, than the minimum, or greater than or equal to it, you can just take it to be 1/2 phi PM, and adding them together will give you phi PM. So the strategy was take two different halves with an open cover and add them together by taking subset neighborhoods of them with half distances. By the definition of phi PM, we have dy f of p f of PM is less than epsilon, because this implies this, and dy of f of q f of PM is less than epsilon. F of p f of PM. Because if it's less than 1/2 phi PM, it's going to be less than phi PM. So it will imply this. So you're going to have this over here. F of p, f of PM less than epsilon. So you're going to have these two things over here. Now you add these two results together, you get the distance of y from f of p to f of q is less than 2 epsilon. Which you can take it to be epsilon because the 2 is absorbed, because epsilon is arbitrary. So you get to the conclusion that this over here, this is of x pq less than delta implies that this is of f of p f of q is less than epsilon, which proves that it is continuous. That's the definition. We have the following theorem. Let E be a compact subset of R1, non-compact subset of R1. Then there exists a continuous function on E that is not bounded. There exists a continuous and bounded function on E which has no maximum. And in addition, if E is bounded, then it's not written here, but there exists a continuous function on E which is not uniformly continuous. Basically. So for case 1, we have E is bounded, hence non-compact. It's non-compact and it's bounded. So we know that bounded and closed is compact. If it's bounded, that means it must not be closed, so it's open. There exists a limit point x not in E, because it doesn't contain all of its limit points because it's not closed. We define the following function: f of x equals 1 over x minus x naught. Then f is continuous on E by theorem 4.9. Because the denominator is not 0 because x naught is not in E, and is unbounded near x naught. Because x naught is a limit point and you can approach it, but you can't get to it. But because you can't get to it, but you can approach it and go to infinity, it can show that it's unbounded near x naught. So that's for the first result. If it's bounded, if we consider it as bounded, there exists a continuous function on E which is not bounded. That's for A. Okay, now for C, the same f in 21 is not uniformly continuous on E. Given epsilon greater than and delta greater than 0, choose x in E with x minus x naught less than delta. Taking t close enough to x naught, we can make the difference f of t minus f of x greater than epsilon, although t minus x is less than delta. Yeah, that's because it's unbounded, right? You can make it greater than greater. This since this is true for every delta greater than 0, f is not continuous uniformly continuous on E. Now, define g of x equals 1 over 1 plus x minus x naught squared. Then g is continuous and 0 is less than g of x is less than 1, because this is always greater than or equal to 0, but it can't be 0 because it doesn't contain its limit point. So it's between 0 and 1. Moreover, supremum of x and e of g of x equals 1, because that's the upper bound. It can get closer and closer to 1 as it goes to this limit point. So you can take the supremum to be 1. But since x naught is not in E, we have g of x is less than 1 for all x in E. So g has no maximum on E. So because it doesn't contain its supremum, that means it doesn't contain its maximum. So it doesn't have a maximum on E, which proves the second statement B, which was this. There exists a continuous bound function on E which has no maximum. That's for the case where E is bounded. Now we want to take the case when it's unbounded and prove the three things again. For A, we can just take f of x equals x on E. It's continuous and not bounded, right? Because it goes from negative infinity to infinity, like this. It's a straight line. For B, you can define h of x equals x squared over 1 plus x squared. Then h is continuous, 0 is less than h of x is less than 1. And supremum of x in E of h of x equals 1, but the value 1 is not attained, since hence h has no maximum on E. Yeah, okay. Now for C, the boundedness hypothesis is essential. If E equals z, then every function e to r is uniformly continuous. Taking delta less than 1 in definition for 4.18 forces p minus q less than delta imply p equals q. Because if it's less than 1, we know that distance between each integer is 1. So that means you're just going to be left with one integer in that neighborhood. So the condition is trivially satisfied. Okay, we now we have the following example. It's a really interesting example. Let x equals 0 be from the closed set. Let x be the half open, half closed set 0 to 2 pi. The half open interval on the real line, and let f be the mapping from x onto the circle, right? Given by this. We know cosine of t and sine of t are continuous. However, the inverse mapping is not continuous at the point 1, 0 equals f of 0. This is because x is not compact in this example. It is worth noting that f inverse fails to be continuous even though y is compact. It's interesting. Y is compact. It has, so I mean that means f inverse has a compact domain, but x is not compact and it's not continuous. Sorry, yeah, it's not continuous. Why? Let me explain why. So imagine you're approaching cosine of t and sine of t. If you're approaching it from t goes to 0 and t goes to 2 pi, right? If you take it from t equals 0 over there, you're going to get that the f inverse goes to 0 when the function goes to 1, 0. From the other side, it goes to 2 pi when it goes to 1, 0. And there's a huge difference between 0 and 2 pi. It's you can't. It's a discrete jump. You can't show that it's continuous. So that's why it's not continuous at that point. Now continuity and connectedness. Let f be a continuous mapping from a metric space x into a metric space y, and let e and x be connected, then f of e is connected. Okay. So the famous saying is that when something is continuous, you can't take the pencil off the paper when you're drawing it, right? This is basically what it's saying. Assume for contradiction that f of e equals a union b, where a and b are non-empty separated subsets of e. This is okay. This is not. This is not by contradiction. We just want to show that if it's not connected, then that means that's not connected. That's what we want to show. This is a mistake over here. F of e equals a union. Okay. Let G equals E intersection F inverse of A, and H equals E intersection F inverse of B. Then E equals G union H. Uh, uh, because they're separated. They're separated. So if you take their intersections, you're going to have two separated G and H, and you're unioning them back together to get E. Because all you have is F inverse of A and F inverse of B that are separated, and you're unioning them back together to get E. And neither G nor H is empty. Since A is an A closure and F is continuous, F inverse of A closure is closed in X. Because that's the theorem we proved. We showed that if it's closed over here too. So G closure is a subset of F inverse of A closure. G closure is going to be this closure over here. Okay, let's just see. G is an F inverse of A closure. G closure, sorry. This is because, okay, G equals E intersection of F inverse of A, and if I'm not mistaken, if you take the closure, you can take the closure of the intersections too. If I'm not mistaken, I have to double check that, but let me just see if give me a second, I'll think about this. Okay, so I'm back now. I had to take a break. Let's just start reading this proof. Okay. Let F be a continuous mapping from a metric space X into a metric space Y, and let E and X be connected. Then F of E is connected. Like as I said before, it's like when you're drawing something and you're not lifting your hand, that's when it's continuous. So we're trying to relate connectedness to continuity. And how we do this, assume again, this is not contradiction, there's a mistake here. Assume that f of e equals a union b, where a and b are non-empty separated subsets of y. Let g equals e intersection f inverse of a and h equals e intersection f inverse of b. Because look, f of e is made up of two separated parts, and f of e is basically coming from e. So if you take the part in e, which is f inverse of a and f inverse of b, you're going to get those parts which will be mapped to f of e, and their union will be exactly e. So you're going to have e equals g union h, and neither g nor h is empty. Since a is an a closure and f is continuous, f inverse of a closure is closed, because as we said, if it's closed here, it's closed here. So g closure is an f inverse of a closure. Why? Because when we're talking about the closure of f inverse of a, actually there's a really good exercise that I'm not sure if I included it at the end, but basically it's saying that f of e closure is included in f of e all of it closure. That's like the exercise. This exercise number 2, if you'd like to check that out. So f inverse of a closure is a subset of f inverse of a closure. So this is a subset of f inverse of a closure, this thing. And we know f inverse of a closure is basically g closure, because we're taking the parts that are f inverse of a that are in e and taking their closure, which is basically g closure. So g closure is an f inverse of a closure, and f of g closure is an a closure. Or another way to view this, I'm not sure though, is that you can take the closure, the intersection of the closures of these things. Yeah, because the closure of the intersection of two closures, so the intersection of x and y closure is the same thing as the closure of x intersection the closure of y. And if you think about it, it makes sense, because you want to see all those limit points that are part of x, that are part of how do you call them, of x and y, and if you take their intersection, you're going to be left with all the limit points that limits x intersection y, if you know what I mean. Yeah, exactly. Let me just think about that real quick. That's actually a good point. Let me just make sure real quick. Let me just make sure. I'm just looking it up online.
No, it doesn't always work. The closure of A intersection B is is inside A closure intersection B closure, but not the other way around. That's how it works. So we can't really use that logic. But the logic we can use here is that you can take uh, G closure G because okay, if you really want to go into detail for this for this theorem, we need to go to that exercise, which basically says f of e closure is a subset of f of e closure. And how that works is that when you have the closure of e and you're taking the function of it, and f is continuous, then you know those limit points are part of e, and since they're part of E and they're limit points and it's continuous, you can, and that means you can choose any delta in that neighborhood and associate an epsilon in the F E closure neighborhood. And that means all the limit points of F of E closure will definitely be points of F of E, all of it closure. That's how the reasoning goes. So if you use that logic, you can get that G closure is a subset of F of inverse of A closure, and F of G closure is a subset of A closure. Because here you just apply F on both sides, right? Because F of H is a subset of B, and A closure intersection B is not empty. Sorry, it's empty. We have that G closure intersection H is empty because this is a subset of B and this is a subset of A closure. So the intersection of these two is closed, and we know that these are part of these two. So the intersection of those two will also be closed. And since they're closed, we're going to have that. These two sets are separated, basically. So exactly, it's G and H are separated. So that means if they're separated, the if continuous mapping, it's also going to be separated when you map it to the codomain, and if they're connected, it's also going to be connected. Now let's read the following theorem. Let f be a continuous real valued function on AB. If f of a is less than fb and f of b, and c is a number such that f of a is less than c less than f of b, then there exists x in AB such that f of x equals c. This is called the intermediate value theorem. Basically, it's something you're taking a neighborhood and a neighborhood here. Basically, you're saying if this is in this neighborhood, it's going to be in this neighborhood. That's basically what it's saying, and it follows from this theorem over here because we just showed that it's connected, and AB is connected, f of AB is connected, and if you apply it again, you're going to see that C there's going to be some x which gives you C when you apply the function to it. Okay, now we have discontinuities. If x is a point in the domain of a function f at which f is not continuous, we say that f is discontinuous at x, or f has a discontinuity. And we have two classifications, the right hand limit and the left hand limit. And basically how we describe it is that we take all the sequences inside coming from the left and from the right that converge to the point, specific point Q. That's how we talk about left and right hand limits. And obviously, if these two are equal and they're equal to the limit at that point, then that the limit exists, basically. And there are two types of discontinuities. The first kind is when f of x from right and f of x from left exist, and again, this type has two other types. It is that f of x from right is not equal to f of x from left, or f of x from right is equal to f of x from left, but it's not equal to f of x. These are the two types of the first continuity. The second continuity is when f of x from right or left doesn't exist. And we have the following examples. F of x equals 1 if x is rational and 0 if x is irrational. This function has a discontinuity of the second kind at every point x, since neither f of x from right or left exists. Why? Because when you take any rational number, we showed that Q is dense in R, right? And we know that the set of irrational numbers is uncountable like R. So you can always fit a value between the 2 points that is either going to be rational or irrational. And so it can either take the value 1 or 0. So you're not really approaching anything from either right or left. That means it's a discontinuity of the second kind. Now f of x equals x when x is rational and 0 when x is irrational. Then f of x is continuous at x equals 0 and has a discontinuity of the second kind at every other point. Because when you approach 0, the rationals are also going to go to 0, so it's going to be continuous. There won't be any discontinuities or discrete jumps between 0 and a point near 0, because it's from right and left. From right and left, it's going to be the same thing. It's going to 0, right? Because the function x goes to 0 and this also goes to 0. Now and every other point has a discontinuity of the second kind, because like we said again, it's going to be something similar to this, so there won't be any left or right limits. And now we have this example over here. F of x equals x plus 2 for negative 3 is less than x is less than negative 2. Negative x minus 2 for negative 2 less than or equal to x less than 0. And x plus 2 for 0 less than or equal to 1, 0 less than or equal to x less than 1. This function has a simple discontinuity at x equals 0 and is continuous at every other point negative 3 to 1. Notice at negative 2, x plus 2 and negative x and negative 2, when you put negative 2 in them, it will give both 0. So there won't be any difference when you're jumping from one to another. But when x equals 0, here you're going to have negative 2, here you're going to have plus 2. So there's going to be a simple discontinuity at x equals 0, because both left and right hand limits exist, but you're getting different values from each point. And we know it's continuous on every other point because we're talking about lines. Okay. Now, sine of, f of x equals sine of 1 over x for x not equal to 0 and 0 for x equals 0. We know that f of 0 from right and f of 0 from left don't exist. That's because you're not really approaching anything. Sine of x is basically cycling from negative 1 to 1, and when you take bigger and bigger values when it goes to 0, you're basically cycling. You're not going anywhere. You're not approaching anything. So neither the right hand nor the left hand limit exists. So f has a discontinuity of the second kind at x equals 0. And we know sine of x is continuous. And we know that this only happens for x equals 0, this discontinuity. So we know it's continuous at every point x is not equal to 0. Now we have monotonic functions. Let f be a real valued function on AB. We say f is monotonically increasing on AB if a less than x less than y less than b implies f of x is less than or equal to f of y. It's basically the same thing as the sequence definition of monotonically increasing and decreasing. So at each point you're setting a border that you can't cross anymore, either increasing or decreasing. Now we have the following theorem. If f is monotonically increasing on AB, then f of x from right and f of x from left exists. Then f of x from right and f of x from left exists for every x in AB. More precisely, f of x from left is the supremum of t less than x of f of t, and f of x from right is the infimum of t greater than x of f of t. And furthermore, if a is less than x less than y less than b, then f of x from right is less than or equal to f of y from left. And the logic here is that it's monotonically increasing. If you want to take the limit from the left and from the right, we know that each point is defined because we said it's less or equal to the other point, right? And we know that this. I'm just talking about the strategy. We'll see the proof later on. There's going to be higher and higher values, and you're going to reach the last value, which is going to be the limit point, which is because it's the point at which it is converging. So if you take it from the left, you're taking the highest point, so it's going to be the supremum. And if you're taking from the right, you're going to get the lowest one, which is the infimum. And likewise, if you have a less than x less than y less than b, then we know that f of x is less than or equal to f of y, obviously. And when you take f of x from right and f of y from left, this is for monotonically increasing functions. If you take f of x from right, then that thing is going to be the infimum of all those f of x's. And we know that f of x is already less than f of y. And if we're taking the infimum, it might even be less than that. And we know that f of y from left we're taking the supremum, and we know it's already bigger than f of x. And it might be even greater than that. So, of course, when you think about it rationally, I'm not talking about a rigorous proof, f of x from right is less than or equal to f of y from left. Analogous statements hold for monotonically decreasing functions. So now we have the proof. By hypothesis, the set f of t, a less than t less than x, is bounded above by f of x, and therefore has a least upper bound denoted by a. Clearly, a is less than or equal to f of x. We must show that a is equal to f of x from left. Let me just check something over here. Yeah, so a is less than or equal to f of x because f of x is the largest value here, and since it's the largest value, if you take the least upper bound, it's going to be less than this higher upper bound because x might be bigger than that lowest upper bound, right? Let epsilon greater than 0 be given by the definition of a as a least upper bound. There exists delta greater than 0 such that a less than x minus delta less than x. Yeah. And a minus epsilon is less than f of x minus delta is less than or equal to a. We get the following by applying f to this. Since f is continuous, since f is monotonic, we have f of x minus delta is less than or equal to f of t is less than or equal to a. Because for x minus delta less than t less than x, it follows from monotonically increasing functions. Combining 27 and 28, we obtain f of t minus a is less than epsilon. So you can just subtract a on each side over here. You're going to get that f of x minus delta is less than epsilon. Since it is less than epsilon, and you're subtracting f of t from it, it's also going to be less than, sorry, if and you're subtracting a from it, it's also going to be less than epsilon. Thus f of x from left equals a, because that's the definition of when we're approaching from the left. The second part of 25 is proved in exactly the same way by considering the set f of t, x is less than t is less than b. And this is basically exactly what I explained over here. It's basically saying it in rigorous terms over here. Now we have the following theorem. Let f be monotonic on AB. Then the set of points in AB at which f is discontinuous is at most countable. This is very interesting. And the strategy here is to associate every discontinuity with some sort of rational number. Between discontinuities, which we choose some rational number. And this shows that it's countable. Suppose for definiteness that f is increasing, and let E be the set of points where f is discontinuous. For each x in E, choose a rational number Rx, such that f of x from left is less than Rx is less than f of x from right. Since x1 is less than x2 implies f of x from right is less or equal to f of x2 minus f of x2 from left, it follows that Rx1 is not equal to Rx2 whenever x1 is not equal to x2. Because you're getting different values of these. You're getting different bounds for R of x, so they won't be equal. Thus we have established a one-to-one correspondence between the set E and the subset of the rational numbers Q. Since Q is countable, E is also countable. Now we have the following remark. The discontinuities of a monotonic function need not be isolated. In fact, indeed, given any countable subset E in AB, even if E is dense, we can construct a monotonic function on B that is discontinuous precisely at the points of E. To see this, list the points of E as xn n equals 1 to infinity, and let C of n be a sequence of positive numbers with the sum of C of n is less than infinity. So what we're doing here, we're taking the set of points that are a subset of AB, and we're taking them to be a sequence, and we're taking another sequence C of n, and we define f of x equals xn is less than x of C of n for a less than x is less than b. That's how we're defining it. So we define a sequence and another sequence, and we're saying that this sequence is a sum. This sequence is a sum of when this sequence is less than this value of x. The sum is taken over n such that xn is less than. If there are no such xn, the sum is taken to be 0. Since the series in 31 converges absolutely, the order of summation does not matter because they're all positive numbers and their sum is less than infinity. The following properties are easily verified. F is monotonically increasing on AB. That's obvious because you're adding positive terms each time. F is discontinuous at each xn in E with jump size f of xn from right from minus f of xn from left is equal to C of n. Yeah, because you're suddenly jumping without any notice. After crossing this border, you're jumping values. So when you're approaching from right and left, it's going to be different, and it's going to give you C of n, because that's what you're adding. That's the jump. F is continuous at every point of AB other than is subtracting E. Furthermore, f of x from left equals f of x at all points of AB. In this case, f is said to be continuous from the left. That's the definition. And the reason why is that the reason why, mm, because you're adding suddenly without any equalities, okay? And that means that when you're approaching from the left, you're taking all the previous values without considering that jump. And since f of x before that jump is all those values not considering that jump, it will give you the same thing as f of x. If the summation in 31 we're taking over all n with x of x n less than or equal to x, we have f of x from right is equal to f of x, making f continuous from the right. Because now x of n is also included in the jump. So when you approach from the right, looking back at all of them, and you're looking exactly at that point, you're going to get that f of x from right is equal to f of x. Okay, now we have infinite limits and limits at infinity. It's basically the same thing as limits, etc., but we're defining it in terms of neighborhoods. And we get the same properties when adding, subtracting, dividing. Okay, this is the exercise I was talking about. We just proved it earlier, but we want to show that it is also a proper subset. And to do that, you can take the set of points 1 over n. It's actually 1 over x if you want to. If you want to make it continuous, you can take the points 1 over x from 1 to infinity. And we know that doesn't contain its limit point, so that means f of e is closure. This is supposed to be closure over here. There's supposed to be a closure over here. Okay. Now we have the following exercise. Let f be a continuous real function on the metric space x. Let z of f, the set of f, be the set of all p and x at which f of p equals 0. Prove that z of f is closed. Okay. So let me pull up the notepad real quick. Okay, so I just pulled up the notepad. Okay. Okay. Let's do it like this. So we want to take the set of points at which it's 0. And the set of points at which it is 0, and we know it's continuous, right? So suppose, is it writing? Hold on. Suppose P is a limit point. Point of z of f what we want to do right now is show that p is in z of f. Now notice, if p is a limit point, that means for all x in z of f, sorry, that means, okay, that means for all epsilon greater than 0, for all epsilon greater than 0, there exists x in z of f such that x minus p is less than epsilon. Let's actually take this to be delta, just to make it neater. For all delta greater than 0, you have x minus p is less than delta. Okay, so we have this, and we know for all x in z of f, we know f is continuous, so we have the following: for all x in z of f, for all epsilon greater than 0, there exists delta greater than 0, such that x minus p less than delta implies f of x um, um, let me just think about this real quick. And for all, let's say for all y, for all p, for all x in z of f, we have the following. We know f of x and we know f of sorry, hold up. Let's remove this part to make the proof neater. For all p in z of f, we have x minus p less than delta implies f of x is less than epsilon, because f of p is equal to 0. Let's write this: f of p equals 0. Right. So if you think about it now, let's say this is the set of z of f, and this red thing over here is the limit point of z of f. We know we can take any small neighborhoods that will contain a point x in z of f, like this. And now for each of these points we can take another neighborhood for which absolute value of f of x is less than epsilon. And you can let delta go to 0, and you're going to have that these neighborhoods of these points will actually lie in neighborhoods of red. So green neighborhoods lie in red neighborhoods. Basically. So that means we know that this thing over here works for every delta, and we can let delta go to 0 and epsilon will go to 0. So what's happening here is that we're using the definition of continuity and the definition of a limit point, and we show that there's always a point delta at p, there's always some delta at p for which you're going to have f of x is less than epsilon, which means that it is continuous at that point, and that when it's continuous at that point, it will give you that it is equal to 0. So that means it is part of z of f. So P is in z of f, which completes the proof. Okay. Now let f, if f is a real continuous function defined on a closed set E in R1, prove that there exists a continuous real function on R1 such that g of x equals f of x for all x in E. So you're taking a function f on a real continuous function f on a subset of R and another function on all of R, and they're equal at those points. And we know that the set is closed. And to prove this, if it is closed and it's continuous, then you can just start from those closed points and add lines, and you're going to get another continuous function, which is g of x. But notice, if it's not closed, it won't work. It won't necessarily work because, for example, take the set of 1 over x from 0 to 1, okay? If you take that, it's continuous from 0 to 1 open, right? Because it won't reach 0 and it's continuous on all of those points. But if you want to take g of x, at that point afterwards, you can't really connect it with each other, because we know for continuity we need connectedness. But we know it goes to infinity, so how are you going to connect two graphs together, right? So you can't really do it with open sets, but you can do it with closed sets. Now we have if f is defined on E. Okay, and also an important thing, these things are called continuous extensions. Continuous extensions of f from E to R1. That's what they're called. Now 6, if f is defined on E, the graph of f is a set of points x f of x for x in E. In particular, if E is a set of real numbers of f, okay. Suppose E is compact and prove that f is continuous on E if and only if its graph is compact. This has a very similar proof to what we did with f inverse of v and v. So you can take so if it's compact over here, it must have an open cover, and it must have an associated open cover there. So if it's compact, then it will be continuous. And if it is continuous, you can just backtrack and say, okay, it's continuous. We use the fact that every associated domain or every associated open domain, open subset of a domain is associated to the open subset of a codomain, and just show that there exists an open cover and prove the converse. Okay, if E is a non-empty subset of a metric space X, define the distance from X to E by P E of X of infimum of A in E of the distance X in A, X to A. So basically the closest distance from that point to that set. We're calculating the distance from X in X to E. Prove that P of E in X equals 0 if only if X is in E. Why? If it's 0, that means this infimum is 0. That means 1 point in this set is 0. That means if it is 1 point in this set is 0, that means 1 point of this set is exactly the same thing as that point of that set, which means that it lies in that set. Prove that PE is a uniformly continuous function on X by showing that for all x and y, x, y, and x, Pe of x minus Pe of y is less than or equal to dxy. And the hint gives it away, basically. We know that P of x is less than or equal to the distance of x to z for some z in E, because this is the infimum, so this is greater than the infimum. It's part of that set. It might also be the infimum, so we just say it's less than or equal to that distance over here. And we know this is less than or equal to distance from x to y plus the distance from y to z. And so the distance from y to z is basically less than or equal to the distance of e to y, right? Because it's the same thing as over here. You're taking it to be less than or equal to distance from x to z. Here, you're taking this to be less than or equal to distance from y to z. So distance of e to x is less than or equal to distance of x to y plus distance from e to y. And if you subtract on both sides, you're going to get that distance from e to x minus the distance from e to y is less than or equal to the distance from x to y, and that proves it. And now we have the following theorem, following exercise. Suppose K and F are disjoint sets in a metric space X. K is compact, F is closed. Prove that there exists delta greater than 0 such that distance of PQ is greater than delta if P is in K and Q is in F. And basically the proof here, the strategy, basically what this is saying is that there's a minimum distance between these two sets, and to prove this we know that the distance between from F to some point is continuous, and we know it's always greater than 0, and so that means there exists some delta greater than 0 such that this works, and they're disjoint, so it must be greater than 0. And if it's not disjoint, then you can show that with a counterexample that it doesn't work. Now let A and B be disjoint non-empty closed sets in a metric space X, and define f of P equals P of AP over P of AP plus P of BP. Show that f is a continuous function on X whose range lies in 0 to 1, that f of P is 0 precisely on A and f of P equals 1 precisely on B. Okay, the range lies in 0 to 1. Why? Because this is always less than or equal to this, so you're going to get it to be a fraction less than 1, a positive fraction less than 1, and we know it's greater than 0, so it lies between 0 and 1. And f of p equals 0 precisely on A. Why? Because if it is in A, this becomes 0, this becomes 0, and this is something over here. This is some value. So 0 over 0 plus something is 0. So it will give you 0. And f of p equals 1 precisely on B. And if it were not to be on A, then this value would never be 0. So it must be on A. And f of p equals 1 precisely on B. Precisely on B, because the only way you can get these two things to be equal is when this is 0, and it's when it's precisely on B. Okay, now if we set V equals f inverse of 0 to 0.5 and f inverse of 0.5 to 1, we can show that V and W are open and disjoint, and that A is in V and B is in W. The strategy here is that you can describe the set of all the function as the union of V with the points 0.5 and the union of W, and we know that the union of V with the point 0.5 is closed. And since W is the complement of that, which is closed, it's open. And likewise, you can take the union of W with that 0.5 and take its complement. That means V is also open. And we know that they're disjoint because 0.5 is separating them. You can prove that by taking their complements. And A is in V and B is in W. That's because they're disjoint, right? So, and they're closed. .5 basically happens when this is equal to this. When this is equal to 2 times this. So that means when P of A of P equals to P of BP. But when that happens, uh, uh, that means it's either 0 or another value. If it's 0, then we know it contains A. And if it's another value, that means that means it doesn't contain A, but it contains some other points. Doesn't contain A or no. Okay. Yeah, okay, no, a simpler way to put this, A is in V because f of p equals 0 precisely on A, and we know 0 is part of the codomain, is part of the domain of f inverse. So it will give you A, and it will give you A with some other points, and likewise for this, it will give you B with some other points. So B is a subset of W2. And this property is called the normality. So any two disjoint closed sets can be covered with two disjoint open sets. And we have this final exercise. A real valued function defined on AB is said to be convex if f of lambda x plus 1 minus lambda y is less than or equal to lambda f of x plus 1 minus lambda f of y. Basically, we saw the definition of a convex set. Here, we're talking about a convex function, which means that when you take the distance between any 2 points, it's always going to be, and when you evaluate it, it's always going to be less than when you take it separately. So what it means is that it's kind of like increasing, because when you take it to be between those 2 points, it's going to be less than those 2 points, right? So when you evaluate at those points, it's going to be less than when you take them separately, and it's going to be equal when you have linear functions, basically. For these conditions, prove that every convex function is continuous. To do this, I'll just write up the proof. Let me write the proof for you. So we're going to get f of 1/2 x plus 1/2 y is less than or equal to 1/2 f of x plus 1/2 f of y. Actually, okay, my bad. Let me write something else. Okay. F of lambda x plus 1 minus lambda y is less than or equal to lambda f of x plus 1 minus lambda f of y for all lambda in 0 to 1. And we're going to get f of lambda x plus 1 minus lambda z. If we can just copy this, I'm not sure how. Let's just rewrite it. So they're equal to lambda f of x plus 1 minus lambda f of z. These two subtracted together give it's going to be equal to, so this thing over here, sorry, it's going to be less than or equal to 1 minus lambda f of y minus 1 minus lambda f of z. For all lambda in 0 to 1. And we can say that we can construct basically over here. So we're going to say we're going to say let lambda x plus 1 minus lambda y equals x naught lambda x plus 1 minus lambda z equals p. So we're going to get that f of x naught minus f of p is less than or equal to lambda 1 minus lambda f of x plus 1 minus lambda f of z, and this thing over here goes to 0. It goes to 0, so that means it's less than epsilon, and that proves continuity. Continuous. Now we get to the second part of the exercise, is that we want to prove this inequality over here, and it's fairly easy. You can basically use a fact. Let me zoom out. You can use a fact that f of lambda x is less than or equal to lambda f of x. So we can take s equals lambda t, t equals lambda u. So we're going to get f of t minus f of s over t minus s is less than or equal to lambda f of u because f of t is f of lambda u, so it's less than or equal to lambda f of u, minus lambda f of t, because s is lambda t, over lambda u minus lambda t. And we just cancel out and we get one of the inequalities. When you want to get the second inequality, basically what we do, what was the, let me just check what was the second inequality. It was this thing over here. So if you want to get this thing, you can basically do this. F of t minus f of s over t minus s is less than or equal to lambda f of u minus f of s over lambda u minus s. But notice that uh, um, notice that this thing over here is less than or equal to f of u minus f of s over u minus s. So we're going to get f of t minus f of s, or t minus s, is less than or equal to f of u minus f of s over u minus s. Why? Because lambda is between 0 and 1. So this will definitely be less than this. And this over here is going to be less than this. But since we know that when you take the function, it increases, it's going to increase more in the numerator than in the denominator. So you're going to get this. For this to be less than this, basically, we know that f of u minus f of s over u minus s, you can just you can do the same thing now. This is less than or equal to f of u minus, we said s is lambda t, minus lambda f of t over u minus lambda t. And with the same logic over here, this lambda is going to be less, and you're going to this is going to be less than or equal to f of u minus f of t over u minus t. This is a proof I came up with myself. All of these are proofs that I came up with myself. Pretty sure it's correct. It could be more rigorous in my opinion, but I think it's good. Actually, I think I could come up with a better proof here. I'll leave that to you, but it's something I thought of myself. So that's it for this video. I really hope you enjoyed it, and see you in the next one.